CS182, 282A, course on deep neural networks. So, um, and as you know by now, the course is actually in a new format, which I'll explain in more detail in the middle of this. I want to do some high-level introduction first, though. So first, the content of the course is about networks, how to train them, how to design them, and can't possibly miss the amount of media around deep networks, AI generally, but really the revolution in AI in the last about 8 years has come from the deep networks and their applications. And here's a sampling of articles. Most very positive, some actually very negative, because there's signs that there are deep and I guess traumatic impacts economically from these technologies. And also possibly existential threats from these technologies essentially taking over society, AI bots that are so intelligent that they consider humans redundant and eliminate them. And there's been a fair amount of criticism from researchers actually in AI that the media attention is counterproductive, and the technologies still have a long way to go. On the other hand, empirically, it seems that that's not very well justified. So anyway, hype is a notion of extravagant or excessive publicity or promotion. Hope, though, is an expectation of fulfillment of expectations and success. So are deep networks hype or hope? Well, let's look a bit more deeply. The revolution arguably took a long time to happen. The same technology that is currently in most deep network learning algorithms is actually pretty old. So already in 1989, Jan LeCun built a convolutional multi-layer network to recognize postcodes or zip codes for the US Postal Service, and it was actually deployed. It ran for many years. And more or less it has a modern architecture. So it consists of convolutional layers, nonlinearities between them, even some normalization normalization. It was pretty simple, but it worked remarkably well, and it improved on the state of the art at that time. And then if we fast forward to 2012, which is the the winning of the ImageNet challenge that year. So it's an image classification task, pretty open-ended and much larger than most other machine learning challenges. That was won by a convolutional network from this time Jeff Hinton's group in Toronto. But perhaps the most remarkable thing is that the architecture was very similar, just slightly different from the Linnet approach, which was 23 years earlier. So, and if you look at this slide, you'll notice that you might be able to see that there's, in successive winners of the ImageNet competition over the years, that's what's plotted in the blue curve there. Before 2012, they were classical computer vision algorithms, and at 2012, there was really a sharp drop. The curve, well, part of the trouble is they actually didn't have an ImageNet challenge. This problem was already too difficult for most machine learning algorithms before that time, but generally speaking, people would see slow improvement over the years, and typically traditional methods sort of plateaued out at some lower bound of performance. The convolutional networks, though, however, once people saw that dramatic drop in 2012, the most surprising thing probably was that performance kept improving after that. It kept going down. In fact, almost anybody before that time would have assumed that there'd be a hard limit at human performance for this task, because it had been the case for almost every other task. But then actually, as you can see from that curve, the performance just kept improving. It sort of crashed through the barrier of human performance around 2015, I think, the Microsoft implementation residual network. And it's kept going since then, and the only obvious lower bound is 0. So what happened there? Well, we'll get to that a little bit later. And as I mentioned, the architecture is almost a Lunette. It's still convolutional. It still has nonlinearities between and some normalization. And fully connected layers on the output. So the ImageNet challenge was the sort of performance challenge that captured most of the media attention and most of the mainstream attention also in research. The big impact, though, in terms of improving beyond human performance is actually a little bit earlier in speech recognition. And here's a scatter plot for I think this is isolated word accuracy from speech recognition from a TIMID, a kind of a voice response system challenge. And anyway, yeah, you can see blue curves. It's not a nice graph over time. It's a scatter plot of different systems, but you can see things change dramatically between the blue dots and the orange dots. The blue dots are non-neural systems, and the orange dots are neural systems. Again, you can see this. Well, I think you can see this orange implied curve just sort of cascading down towards a much lower error. And in fact, for connected word recognition, Google Machine Learning Group achieved, essentially human performance a couple of years ago. And again, it's still continuing to improve beyond that. Language translation in natural language, there was a similar story. I guess what I meant to say on that previous slide is that speech recognition actually was slightly the first area in which neural networks really went beyond human performance. And almost the last topic I'll mention is machine translation natural language, where the sort of evolution of a new kind of neural network, a sequence-based network, very rapidly improved performance on natural language tasks. And already those sequence models in neural networks, in 2017, this plot is from 2017, and you can see the best neural system, so that's the second column from the right there. The best neural systems were already improving on non-neural systems in almost every one of these tasks. But there's been a similar revolution in the design of neural networks for natural language processing since then, and actually the performance gap is much higher now because people move from sequence models to what's called a transformer or attention-only architecture, and that's having an even bigger impact. So the last topic I wanted to mention is game playing. And this has perhaps led to some of the anxiety about impacts of deep networks. So in 2013, DeepMind, which was then not part of Google but became part later on, developed a sort of machine learning player that could play Atari games, console games for a simple console, at roughly human performance. Human expert performance on 6 of the games and not too bad on the others. But an interesting part of that design was it was a similar architecture, same initial parameters, and it was customized simply by being trained on the game itself. It was basically the same algorithm running on all those different games and learning to achieve near human performance. So that's kind of interesting, but before that, there hadn't been a whole lot of interest in Atari games. It's not obvious that that's a very significant achievement. However, a system a couple of years later that combined deep network analysis of board positions with an efficient search strategy, Monte Carlo tree search, a system called AlphaGo defeated a former world champion at the game of Go. And I think most of you probably know that the Go had been held as probably an impossible threshold for machine learning systems. Machine learning had gone way past human performance on chess, but the combinatorics of Go were massively larger. So machine systems which relied heavily on brute force search were not expected to approach human performance on this task. But what happened was that the system achieved perhaps, I guess, superhuman performance on board evaluation using deep networks. And when that was combined with actually quite novel kind of tree search that was not deterministic, people achieved this new tier of performance. And again, as with the other examples, it really didn't stop there. And in fact, things moved very fast after that. And the developers, DeepMind developers, kept improving the system. And already a year later, it defeated the current world championship very decisively. And although by that time human players were preparing to play against machine systems, and the machine systems had already have become master players at Go, which means that human players were studying now the moves from these new systems, it really wasn't enough. And the rate of improvement year by year of these systems is very dramatic. And so the world champion commented that the system's improving too fast. And it's really like playing a different player from the previous year. So, and although humans are still studying the performance of AlphaGo, AlphaZero on these games, it's at the point where it's becoming effectively impossible to understand even what the system is doing. There's too much of a gap in capability. But nevertheless, there have been a lot of interesting things learned from analyzing these machine systems. Even more recently, the same group is building systems that don't even require expert knowledge about the games. I think you might have heard, I guess AlphaZero now learn to play human-level chess without any sort of background in chess. It basically learned all of the standard openings that humans have, learned over centuries by simply playing itself very rapidly. So anyway, so these systems are quite remarkable. And again, another milestone recently was in 2018, different group, OpenAI, with a similar agenda, achieved very high expert performance against human opponents in a cooperative game, which is Dota. So here the players actually have to coordinate with each other. Again, this was one of the barriers that some people held up as something that machines wouldn't be able to do, and yet rather quickly that barrier was crossed. I don't think it's superhuman. Does anyone know, actually, whether the Dota agents have actually won? I know they're very close to winning against world champion teams. Okay, and not surprisingly, because of some of these results, you can see there's not a big delta between these kind of systems and systems that could, manage combat in real-world situations. Actually, let me play the video. That will probably make this more obvious, hopefully. Shoot. All right. Sorry, that was lost in translation from PC to Mac, I think. I'll make sure that there should be a YouTube video linked that you can look at later on. Anyway, Dota looks a lot like combat. It's primitive combat, but agents are, firing weapons at each other and trying to do integrated, coordinated attacks and flank the opponent and so on. So that did trigger a lot of concern around the risks of AI. Lots of thought leaders have, suggested and invested money in efforts to study the impacts of AI. So there's a subgroup at DeepMind that is focused just on the risks. And at Berkeley, we have the CHAI project headed by Stuart Russell. And Stuart, of course, wrote a book recently about risks of AI that's been very well received. And CHAI studies both existential risks of AI and also ways to build validatable AI systems that you can prove things about, prove safety results about. So that's really a new but rapidly growing thread in AI research. Okay, let's see. All right, so to answer the question, is it hype or hope, what would you say? All right, my answer would be yes. So yes, there's some hype, there's some exaggeration, but people highlighting the hopes and potentials of this technology are clearly right as well. So apart from some of the negative press, if you look at, for instance, actual economic growth and investment, this is just for computer vision, investment by companies in the technology, you can see it's clearly growing currently at an exponential rate. This is true actually now in almost every business segment. The umbrella term for this is digital transformation. It's the notion that every business really has to be reworked on a substrate that uses all of the data that they have, uses probably some IoT and sensing to capture more data, and then uses AI techniques to optimize logistics, do better marketing to customers, perhaps even better strategic product design. Okay. And actually, part of the reason I would argue that some of the experts in AI now arguing against the potential of technology is that they have a great track record of being wrong going back to the 1960s. So this is a report from MIT, from Seymour Papert, the developer of Logo, among other things. But it says that they defined a summer project, which is to create a significant part of a human-like vision system. So in other words, solve computer vision. The task would be solved because it could be segmented into sub-problems which will allow individuals to work independently and participate in the construction of a system which would be complex enough to be a real landmark, the development of pattern recognition. So that was 1966, and they tried, and well, after 5 decades though, I think it's fair to argue that they've made a lot of progress. But their predictions of when that progress would happen took a lot longer than a summer. So, yeah, so there were some actually negative consequences, though, of some of the optimism early, which is industry tended to onboard fairly easily to the idea of AI systems being very powerful and very useful, and invested money in it, and startup companies went that route, and unfortunately the outcomes were mostly bad. The early approach to AI typically involved simplifying the problem in a way that actually caused the technology that was developed not to actually transfer back to the real world. Yeah, so actually just let me go forward. And also, yeah, there was the critique that started pretty early was that systems, for instance, that just do computer vision or solve one problem very well are not generally intelligent. But that notion of general intelligence has been really mostly counterproductive in the sense that people arguably are generally intelligent, but societies are actually constructed in the way that they are based on the sort of specialization of human expertise and a partition of labor, if you like, so that people with very advanced expertise are working together and cooperating. And, you know, general intelligence too, people tend to sort of opportunistically switch between the capabilities of human beings as a race versus machines as individual learning systems. Anyway, let me go ahead with this. So again, if we look at performance from some of these systems, shift from classical to deep networks did lead to a kind of a qualitative shift in the performance. So something really did happen. So arguments that were made about AI systems before about 2012 really shouldn't be relevant to what happened after then. Okay. Anyway, so these new technologies do create a lot of opportunities virtually everywhere. Digital transformation is the idea that significant changes will happen in every industry, and most companies are investing pretty significantly in the cluster of technologies. Includes cloud and IoT in order to capture and warehouse the data, and then AI techniques in order to leverage it. Okay. And I mentioned risks before, and there's a lot of ongoing discussion about it. So there's significant research efforts now focused on risks. Also, I guess, deep fakes, bias in AI systems, as well as the existential risks, meaning wiping out humanity, that have been highlighted by Hawking, Elon Musk and Bill Gates and others. Okay. So Jan LeCun, we saw him a little bit earlier. He was the developer of the LearnNet back in '89 and one of the leaders, and received a Turing Award this last cycle. And his characterization is that deep networks require an interplay between intuitive insights, theoretical modeling, practical implementations, empirical studies, and scientific analyses. At this point, they're not nearly as cleanly understood as most other areas within EECS or statistics. That is, they work very well. There is plenty of theory that one can use as a lens through which to view the behavior of deep networks. But generally speaking, the theory, or there isn't really a set of theoretical ideas from which you can fully explain and perhaps optimize performance of these networks or design them. So nevertheless, it's worth striving for better theoretical understandings, and some of the improvements have come from those understandings. Anyway, we try to, though, follow this kind of insight, which is to use some theory where appropriate, look at best practices and designs which have proven themselves, and also use visualization where possible as a means to understand what's going on in these complicated networks. Okay, so we're moving into the logistics of the course itself, so I'll try to leave some gaps for you to ask questions if you want to. So our goal is to introduce deep networks to a broad audience. It's mostly EECS. By broad, I mean, there's sort of a theoretical and a practical component. We want to review some of the principles, design principles, some of the theory, and also visualization for understanding deep networks. And develop some applied skills in designing or reappropriating existing designs for applications. There are some textbooks. Because the field's moving very fast, the textbooks get left behind very quickly. It's very hard to find there really isn't a comprehensive source as kind of a reference for this material. So last time we relied on some of the books that have been written, on some research papers, and of course the lecture notes. What we did end up doing is bolstering those archival materials with discussion section content, and really the discussion content delved most deeply into some of the content, and it was the most relevant to the course. So we're pulling some of that content back as typed or written, not lecture notes, but reference notes for the lectures, so that hopefully you have a better reference than, say, research articles, which we relied on a bit last time. Relied on too much, probably. So this is based on feedback from students in the course last time that we should have something. If we don't have a textbook, we should at least have pretty thorough and detailed notes for each lecture to supplement the books. All right. So, and although we don't have very satisfying theoretical understandings of what's going on a lot of the time, there have been some nice visualization examples developed that can provide insight. So this is an example of how different network optimizers work, whether or not they use momentum in their optimization. And they're optimizing some kind of loss surface. So it represents the loss or error of a particular network as it's training over time. All right. So logistically, the course will be run entirely through B courses. I mean, we'll use Piazza also, but Piazza will be the discussion format. It won't be there won't be other materials there. So hopefully you can just see the course through your B courses dashboard. We use the home page as the master link for everything. There is a syllabus page which is hard to customize, so we don't use that, but you'll see assignment deadlines there. But I would say most of the time it's better not even to look at that, because the assignments will also be posted, the deadlines will be posted, and the links to the assignments will be included on the home page. Because we try to make things as public as possible, the assignments are actually typically a combination of a web page and a B courses assignment. So you really want the link to the web page first, which explains the assignment, and then the assignment link within that, which is the B courses assignment, contains the submission instructions. So in other words, going from the home page will always get you to all of the content that you need. If you use the syllabus page, you'll only get links to basically the submission instructions for the assignments. So we recommend you actually not use that. So the homepage on B courses contains the course schedule, and you can see that lecture notes for each lecture will be there, readings will be there, and then any assignments along with deadlines should be there. I don't know if, yeah, you can see some of the assignments, but the assignment going out and then also the due date on that right column. So any questions so far, by the way? All right. So at high level, the course has a breakdown like this in terms of content. The first couple of weeks will be reviewing ideas from general machine learning that are most relevant to deep networks. The next, roughly 1/3 of the course is around convolutional networks and computer vision. It includes a little bit more about optimization actually as well. That's perhaps the classical core material in deep networks. That's where the majority of the research and development has been. Then the middle third was going to cover natural language. Arguably a smaller number of architectures have had a very big impact. So we'll look a little bit more there at applications there. And also we'll fit in some material around adversarial networks, both adversarial networks intended to fool or deceive a learning system, but also adversarial methods as a way to actually generate better, more naturalistic artifacts. Those two kind of go together. There's, you can think of adversaries playing a game. One is trying to fool the other. The other opponent is trying to, create an artifact that looks more realistic, that can fool the adversary. So those kind of complementary techniques have led to some of the amazing, both good and bad, both the very convincing synthetic images, deep fakes of people saying things they didn't say, etc. And finally, in the last third of the course, we'll be looking at imitation and reinforcement learning. Okay, any questions? We'll also look a little bit about probably Well, in between 1 and 2, we'll have some lectures about trustworthiness and fairness in deep networks. Okay. So we do want people to get some hands-on experience and familiarity with networks. So the grade and the workload of the course includes class participation. We'll measure that differently for different sections of the course. There'll be 2 midterms to assess sort of archival knowledge. We'll have a final project, a group project, and 4 assignments. So 4 kind of significant network development projects interspersed through the semester. Okay. And it's currently optimized for EECS undergrads and grads. It does rely on some statistical knowledge or machine learning knowledge, not really requiring 189, but it's very helpful to have had 189 or a similar stat course. All right, so we won't have discussion sections this week. There isn't a whole lot of content going on this week, and you know, by Thursday's lecture, you'll probably have some questions and things to sort of ask about, and so discussions will start next week. All right, so the big change from last time is that we're migrating to this split format with 2 different sections and 2 very different formats. So why did we do that? Well, I think you've noticed as well as we have that our big lecture halls for very large classes are mostly empty. They're even empty when classes that don't necessarily webcast, which is disturbing. So it suggests that, you know, there's a lack of interactivity in massive classrooms. And as you might expect, if you have, you know, 150 wheeler with 700 approximately seats and only 100 people in there, or 150, some of the people, on average, the people are way far away. And, you know, it's not a great experience. We'd like to sort of get back more towards a traditional kind of classroom experience where students are either in the classroom or not in the classroom, but the classroom's sized for the number of students that participate. And a little bit more than that, the GSIs have been sort of polling and keeping track of who's in and who's not in class in previous offerings, and it does seem that most people either attend or don't attend throughout the semester. So it suggests that that's a very suboptimal use of space at the very least, and arguably the content's not being delivered very well, because if you optimize content for in-class delivery and then it's being consumed through a web recording, it's really pretty inefficient. People don't normally design web content the same way they design in-class content. So it leads us to having these large and mostly empty classrooms. In fact, the majority of students are consuming the recorded lectures instead of going to class, but the lecturers and professors are writing the content for that in-class format. So that's kind of not ideal. And not really related to these classroom or format issues, but very large courses end up having a workload that's dominated by logistics, dealing with exception scheduling, just operational issues, rather than pedagogy. Those terms are linear, so it's inevitable, linear with the size of the class, so it's inevitable as the class gets big enough, they will sooner or later dominate, and they do in practice. So, all right, so we're trying these L and W sections. The L section, which is this one, for 182, well, we can require attendance. That makes more sense than just doing the same old thing and giving people an option of attendance and then not having them waste that as well. We would just have an even more smaller, more empty classroom. So we require attendance so we know that people are making a commitment to coming and also that they're interested in coming and getting the material delivered in an in-person format. And we're trying to encourage interaction, and I need to do a bit more work, I think, on that. But also the content that we create for consumption by the other section, we can do a little bit more optimization for online delivery, which you should see that starting from the next lecture. And so these are the responses that are related to, classroom resources. The other piece is that we're trying to migrate more of the workload away from the academic staff, the professor and the GSIs, to a course manager that is a staff person who is, more like a student services or advisor type person, who can just focus on and is better equipped to focus on those logistical issues, while the staff then can focus on pedagogical issues. Any questions yet about the format? Also, we'd welcome just any input on the format or things, because this is an experiment. It's going to be an ongoing experiment. So any feedback, good or bad, we'll ask that obviously from the W people as well. We'll keep asking it since you may not have much of an opinion yet, but we do want to get your feedback on it as well. Yeah?
If there's positive feedback to this format, would it be considered for other classes potentially in the future?
Well, that would be the idea. I mean, so in particular, the course manager, it seems likely that the course manager, it's a full-time staff person. The person doesn't have to focus on just one course. They could be shared among several courses. And in fact, our course manager is helping out with 188 and I think 61B also. So the thought is to, but in this semester it's not necessarily, trying to offload a lot of resources. It's more observing those courses which are very efficient. In particular, 188 is already very efficient in terms of the instructor. The workload's normally carried by a sort of a super GSI who's been with the course for many semesters. Now, unfortunately, super GSIs, they're fantastic and they just get better and then they graduate and leave. And so again and again and again, right? So that model has, it can be good, it works well, especially if you can get the super GSIs relatively early and keep them around for a while. But you want them to go as well. You don't want them to stay there. So, we hire a full-time staff person, they can stay there for 30 years or something. So, and they continue to accumulate knowledge about this, and then hopefully things can be better in a number of courses. The way Berkeley and most departments work is we never tell instructors really what to do, but they tend to imitate models that seem better. So, really we want to we want to try this out, get feedback, maybe I don't know if we can do objective measurements, but we'll certainly solicit feedback from people about what they think of the model. And it certainly would address a lot of issues in terms of workload and scale, hopefully. Hopefully make the teaching more pleasant for the academic staff, and also hoping to get some value for the students. That's more of the challenge and more of the uncertainty, is how well it works for students. Yeah, question?
Do we get access to the webcast as well?
Yeah, you get it. Everybody can pick and choose what they look at. There will be just normal video recording of the lecture. In addition, the PowerPoint slides have audio on them. And from next lecture, hopefully they'll also have little mini, quizzes is a strong word, but they'll have kind of optional feedback type questions so that the browsing of the content after is not entirely passive. We'll encourage people to use that format if they're in the W section. But just as with the faculty, we're not going to force people to use a particular format. We'll try to get feedback based on what people did, though, at the end. And again, to keep reiterating, you are the students and you know better than us how well this is working, and if you have ideas about how to make it better, we'd appreciate that. Okay. All right, so here's the course staff. So that's me. Let's see. Did any of the GSIs stick around? All right.
I think they're outside.
Yeah, they're outside on the door. All right. Anyway, well, you would have seen several of them on the way in. Michael David Sasson, you might be a bit confused because he was, until recently, the scheduling officer for computer science. He is moving out of that position to be a course manager starting from this semester. And we've hired one course manager. We have funding to hire 2 people. So there will be hopefully another person online soon. Oh, okay, so here are the GSIs actually. So David is on the left at the back there, and that's Roshan next to him. And Forrest is in the other back corner, and then Philippe is next to him.
Everyone.
So we have the other 2, actually, there's Haji is there also. And Aravind he's giving a talk in the South Bay this morning. And Michael David had another commitment from way back, so he can't make it, but you'll see him around. He will also hold office hours. So, logistical questions, best to see him rather than the course staff. But don't see him for content. He's not a deep networking person. So for content questions, it's me and the GSIs. All right, is that clear? All right. You guys can seat or go, wait outside, whatever. If there's no one coming in, you could just sit. We have enough seats anyway. All right, so you definitely need some calculus and linear algebra. We're talking about high-dimensional optimization tasks. So Math 3 and 53 or 54 are very important. Some kind of probability and statistics. Seems that 70 or 134 is enough. There's likely to be a number of other stat courses. If you've had anything, let's say 140, even E126 I think would be good preparation. You should be able to use your judgment. I mean, the requirements would be similar to 189, a little bit less, if anything. Okay, and certainly having 189 helps, but it's not required. We do a self-contained presentation of concepts from optimization and machine learning at the beginning. And really, it's somewhat narrow in terms of its scope, in terms of analytical tools that you need. But certainly you need some programming fluency. 61B is a good base. Although, in some ways, almost overkill because Python's being used almost universally for defining and optimizing deep networks. So we'll be certainly doing that. Okay, there's the course number. As I mentioned, B courses is the pretty much sole source for content, apart from discussion on Piazza. That's my contact info, class time. The Piazza's live, so please sign in. You should just be able to sign into the course. I think we had a little bit of a glitch so far. The people from the W section haven't been joined with the L section. Anyway, just maybe send Michael David a message to say his email is in the B courses page if I don't have it on the slides, which I don't think I do. But send him a message if there's any issues with accessing the content. And the section times are and office hours are just being added to the main page. You'll see them appearing certainly before next week, but probably not there yet, all of them. So for webcasts, we're doing the webcast within EEC, so there'll be a YouTube channel with the course number in it. You should just be able to search for the course number. I don't think it's ready yet. And so we'll have augmented PowerPoint slides. The slides have the narration in them, and they should also have some kind of interactive mini quizzes in them from next time. Okay, Zach, any questions about that? Right. Oh yeah, so we will be assessing attendance. We're not completely sure what the best method is. iClickers is one option, although they're probably overkill. But how many, can I get a hands up of how many people currently have iClickers? And how many don't? It looks like, all right, so maybe a third have them. All right, we'll get back to you soon. I'm also checking if the bookstore can get enough of them. All right, so we have to still figure that out for in-class attendance. I think it's going to be a bit less of an issue moving forward, but anyway. Okay, so, you know, the sort of skill of designing and using deep networks is very much a hands-on skill. So we'll try to give you experience with some of the important designs through the assignments, and then your project will be a little bit more open-ended application of ideas to a non-trivial problem. And it will run for about 2/3 of the course. And you should be approaching the project in a team of 3 to 4 students. And it can be combined with other course projects, although at least for the for the undergraduate versions of the course, we will be constraining the topics of the projects to a fixed set of Kaggle challenges in order to make the grading more fair and, yeah. So, yeah, we encourage people to open source their projects, but not use other people's open source projects. And you'll check in the GSIs. Just because you'll have other workload, it's important to have check-ins to make sure you actually are making progress from the beginning. 3 to 4 person project, that's quite a lot of work. You've got to spread it out over the semester. Don't try to do things in the last week. And there'll be a video and a report due at the end of the semester. So the difference from last year is that the 182 undergraduate projects will be limited to the set of Kaggle projects, so we can just makes it a little bit fair. It also makes it easier for the GSIs to give appropriate suggestions and feedback and help. The graduate courses will not have that restriction, so those would be more like research projects that you're free to choose. Yeah?
Since you did say that it consumes about 2/3 of the semester, will the Kaggle challenges for the final project, would it still apply to some like NLP or DeepRL, or will it just be like computer vision?
Yeah, no, that's a good question. So, yeah, no, we'll probably have one of each. So, but yeah, you'll be in a sense sort of jumping ahead to the material. Material will be there from, let's see, we can put all the material up. I think it might already be up, the old lectures. I'll double check. But yeah, it's a challenge. I mean, for the project, you don't need to build your final network right away. We encourage you to sort of wrangle your data first, pre-process it. You know, those are the first couple, 1 or 2 milestones. We encourage you to compare with a baseline model. So in terms of like designing and coming up with your own solution, it'll be not, you don't need to do it that early. So hopefully by then you'll have some ideas based on course content. For instance, if you want to do an RL project, hopefully you'll see at least a bit of that material before you really need to apply it. But yeah, yeah, there is a bit of a challenge there if you want to do a project on that later material. Okay. Okay, so well, yeah, go ahead.
Sorry, from the previous slide, for the teams, can we have people who are in the web in the class, or is it only
We hadn't considered any kind of restriction like that, and I don't see a reason to not allow that. You can, for obvious reasons, only do one with other undergraduates if you're an undergraduate, or other grads if you're. We had that rule before, though. But I don't see any reason to not be able to work with. Yeah, I mean, yeah, there really needs to be a reason to not do that, because, by which I mean we really want these two sections to be equivalent in everything else. So I don't see any. We would like not to have to make any partition like that. Yeah.
Is that teams for all the projects or only final one?
Not for the assignments. No. No, those are.
Projects throughout the semester.
Yeah.
Okay.
Yeah.
Does that mean the assignments are individual?
Yes. Mm-hmm. Anything else? Yeah.
For participation rate, since the W sections are not coming to lectures.
You know what? I'll try to repeat your question. I forgot to throw this around actually, but I'll just repeat the question. So go ahead again.
The participation rate?
Yes.
Since the W sections are not coming to lectures.
Yeah, so for participation grade, how do we measure that for the non-lecture section? Well, we rely on Piazza, people coming to office hours and discussion. We can still keep track of that. But mostly it's been Piazza in the past, and a limited number of students that are regular attenders at discussion or GSI office hours. Yeah.
Speaking of the difference between lecture and web, there's a decent chance that lecture students self-selected in the sense that they generally have higher grades. So will be graded as a block, or will it be the lecture students are graded against the lecture students, the web students are graded against the web students?
No, I mean, there's no, that's an interesting hypothesis. I mean, one could hypothesize the opposite actually, but I don't know. And everyone will be on the same scale. Everyone will do the same midterms and assignments. So no, we're not doing any partitioning like that. Okay, but it'll be an interesting thing to measure at the end. Yeah.
So does that mean the participating grades for the L section is based only on lecture then?
No, we will also look at the other factors as well, so that it won't be a different kind of participation. You will also be expected to help out with Piazza, but we'll have this other metric that is easier to quantify. So yeah, you're automatically participating more, but we still measure what you do outside of this class. Yeah. I guess, all right, so to be fair, because you're automatically participating more, the participation grade scoring won't be identical of necessity, because, we do want you to, a piece of that for the L version will be how much you attend lecture. Does that make sense? All right, but it will end up being pretty small. Okay. Let's do a time check. So, so there's a very nice online book from Yoshio Bengio, another one of the Turing Award winners for, Bengio, Jeff Hinton, and Jan LeCun. We've all seen some of their work already in this lecture. Yoshio Bengio is in Montreal, and he has one of the three, really leading groups in this area over decades. He's the author with Ian Goodfellow, who's the inventor of the adversarial networks that have been a mini revolution in synthesizing artifacts. They co-authored this book, which is a nice online book, which is linked from their course homepage, and gives you some of the history of the evolution of science, actually, and deep networks in particular. So if we go way back, before there were even digital computers, there was an area called cybernetics. Came immediately after the war. People were very concerned with military applications especially. It's Cold War time. And there isn't yet a big science funding infrastructure in the US. And it's just starting to bifurcate into military and non-military applications. Anyway, cybernetics was very active at that time because it was building on control, the area of control, which had been extremely important in the Second World War as a technology for aircraft and weapons. So, and cybernetics was pretty heavily influenced by the architecture of brains and animal brains. It's the time of John von Neumann and other leaders who really developed the area of modern signal processing. At that time, though, it was also the kind of dominant paradigm in computing as well. Then in the 1960s, things moved digital. People discovered that it was actually very difficult as you scaled up with analog machines to have them give you reliable values throughout a complicated network, so values drift up and down and so on. They also don't go very fast because analog values, there's always capacitance and delays in these systems, and so they're actually both slow and had low reliability. On the other hand, when people switched digital, they could kind of drive signals around and voltages around without much attention to exactly what they were. It led to overall much higher performance, and that was the era of digital computers. So in other words, we steered far away from, the architecture of real brains towards the sort of purely artificial kinds of computing systems. Then in the 1980s, there was a swing back the other way, as often happens in research. And a lot of authors, Jeff Hinton was certainly one of them, became very active in studying what were called connectionist networks, which were mimicking brains again. They were complex and nonlinear, and they used backpropagation, and they also used genetic algorithms. So the work had some successes, but relatively pretty modest impact in practice, apart from a few examples, including the LoNet example. Okay, but connectionism was sort of shoved to the side largely by more formal techniques in machine learning. Computational learning theory really developed rapidly, but it was influenced more by decidability and computer theory results. Effectively, it was the analog of decidability for learning. What things could be learned at all? How do you define, worst case counterexamples that are difficult to learn? And some very negative results, actually, about connectionist or neural systems. So those results really sort of pushed away or suppressed research in connectionist architectures for quite a while. Okay, but then from about 2006, where there were dramatic successes in speech recognition, and then later on computer vision, deep learning just took off and generated these massive improvements in really across the board in applications. They were characterized by end-to-end training, meaning that you didn't need to specially engineer the features in the learning system as people had previously. You just put data in and had labels on the output, and you trained using gradients. They seem to work best with big data sets. The bigger the data set, the better the performance. And that's part of the reason this process really took a while to happen, because people needed the big machines. Arguably, some of this was also leveraged by availability of cloud computing and cheap on-demand machines from Amazon. But anyway, things really took off from that point once again. So if we want to put that on an approximate graph, there were kind of these three phases, starting with cybernetics and then connectionism and then the current modern phase. And in between there was this winter where things, well, you can see it yourself. This is actually a histogram of publications that could be labeled as around deep networks or neural networks or connectionism. So it started going up, then it went down, then it sort of took off again. Okay. So just reflecting on what happened in terms of that, I mean, you would say, well, how did that happen? How could people have proven that these things don't work, and then all of a sudden they work? That's not good. How did that happen? It's still the case that simple neural networks are very limited in terms of their worst case performance. That is, there are relatively simple functions like parity that are hard to compute with small, in particular bounded depth networks, including neural networks. So, and in also training a deep network, like training it to its best performance is NP hard. So that sounds very bad, right, to a normal computer scientist. So why do we even try? Another negative result is that the training of deep networks is purely, almost always, purely greedy training. That is, you compute the gradients of the loss with respect to the parameters of the network, change the parameters by a small increment along the gradient direction, which should improve the loss, right? But it's a greedy method. And greedy methods, in a sense, had been disproven in the rest of AI in the sense that most non-trivial problems in natural language, or to some extent even in computer vision, as soon as you get to, let's say, labeling images with classical methods, it becomes very combinatorial. You have to enumerate labels, but you have to enumerate possible translations for words and do a search tree, or you have to enumerate mappings from objects, areas of the image to labels in a way that matches constraints. So anyway, it looked very combinatorial, and yet deep networks are relying almost exclusively on greedy approaches. Just doesn't seem like that's a fit there for AI problems as people understood them. Yes, and also the dominant paradigm just before the deep network rocket taking off was graphical models from probabilistic reasoning, as essentially they encode joint probability distributions taking into account dependency, and they inevitably represent the human or machine learning expert's model of what the system is doing. So, a variable A might encode income, it might influence, neighborhood D. But anyway, the models are very explicit in terms of what the states and variables encode and on their dependencies. So it implies that then you take one of these networks, do some inference, which means computing the actual numerical probabilities of them being in various combinations of states, then those probabilities are pretty easily interpretable. And you can compute conditional probabilities and all kinds of things from this network. So anyway, it leaves you with a very good understanding and ability to query this model when it's a classical model. And anyway, those kinds of models did lead to improvements in a number of areas, collaborative filtering / electronic marketing in particular, in natural language certainly as well, parsing and translation. So, but in deep networks, the approach is essentially the antithesis. You create a big network with an architecture that typically works for that kind of problem, but it doesn't work for the most part because you have a particular understanding of what the network means. And in fact, once it's trained, it's in general completely cryptic. Not always, but most of the time, it's difficult to interpret any particular neural node activation in terms of something about the input. Okay. But actually, if we think about it from a different perspective, it seems almost obvious that these networks could work, or at least plausible. So the state of the art in computer vision, you know, before people went to neural systems, was that when you process an image, you didn't sort of go straight from pixels to a label, or you know, that's a horse or a tree or something. There are several discrete steps in the middle, and these had been perhaps most carefully articulated back in the 70s by David Marr and his group at MIT, based on not actual architecture of the brain, but psychophysical experiments where you would take live human subjects and expose them to various images and kind of try to isolate the effects of particular stages in this assumed pipeline and try to discover what the pipeline looks like. So his group did a lot of work along those lines, and they concluded that probably there are several discrete stages that include this primal sketch or edge image first, with a little bit of annotation on the areas about what they are, and then a kind of 2.5D construction, which is like a viewer-centered or depth map construction, and then a kind of view-independent internal 3D model of the object, and then an interpretation of its shape and purpose. So, so that does suggest that that there are advantages to having some kind of architecture for computer vision that has many layers in it. And secondly, that you can probably reuse those features across different applications. A second reason for the success of deep networks, and now I'm focusing on the deep part, the fact that the networks are deeply layered. Deep layering does allow you to easily learn hierarchical concepts. And of course, making sense of natural language seems, at least in part, to require interpretation of the language as a tree of grammatically well-founded objects and their relations. So noun phrases, verb phrases, etc. So, and finally, if we zoom way out and look at human learning science, it's generally acknowledged that humans learn incrementally in terms of understanding and building up layered representations. That is, let's say for chess, you learn, first of all, what individual pieces do, and over time you learn, if you like, patterns of good or bad positions on the board, strength in the middle and weak king side or queen side, and you know, many layers beyond that, and that's how you get to very high levels of performance. So it does argue that a good general representation system should be able to layer it and learn in kind of, what's the word, learn very general kinds of abstraction on top of earlier abstractions. Yes. Well, and one of the big surprises, perhaps, or the biggest surprise, has been that you know, greedy optimization methods are still the dominant paradigm in deep network research, and they seem to work. Arguably, they don't just work. It's not enough by itself to just optimize some ad hoc network. It does seem to be that this works best when the network is over-parameterized, meaning it's got more parameters than it really needs to solve the problem. Because if it had exactly the right number of parameters, there may only be sort of one optimum solution and not many others. But the presence of more parameters, so more, you know, more layers perhaps, or more convolutional filters that are wider than they need to be, those kind of redundancies, although redundancy is often not a good thing, it does seem to help with deep networks. And formally, people have shown that when you add more parameters, it doesn't really change the best solution, but it seems to create more locally optimum solutions near in performance to the best one. So it doesn't make it easier to get the answer right. It makes it easier to get an approximately right answer. Okay. Okay, so one more topic. Any questions? Yeah.
Yeah, I understand the redundancy part, because on one hand we're saying that the more the better, and on the other we're saying that if there are more parameters, then there are more local optima. So
Yes, that's. I wouldn't. Not with complete generality, but it's been it's been demonstrated on a sort of important and canonical case of these kind of convolutional networks that adding more parameters gives you this cluster of local optima.
So that's not a good thing, right? So in that case, how
Why is it not a good thing?
Because more local optima means that it gets stuck in the
Yeah, it gets stuck, but it's pretty good. That's the thing. It's the with deep networks, you have an opportunity to make the network better by a variety of means, including using more data or just training for longer. So it's almost the case that you don't ever really get to an optimum solution, in the sense that if you had more data, you would also get better. So investing that time to push maybe a suboptimum optimum further down often gives you in the end the same result, or almost as good result. Later on we'll see some interesting techniques called distillation, which take one other corollary, though, of the fact that you're only at a local optimum means that even if you just train a bunch of these networks and aggregate their results by voting, it's better than each individual network. That's very expensive, but you can make it almost, well, essentially free by distilling, which means you take a bunch of those trained networks and then train a essentially correctly parameterized network, so a much smaller network, not on the data, but on the votes of these other networks. In fact, they're softmax outputs, they're soft outputs. Those data have less sort of susceptibility to local optima than the original data set does. You essentially, it's something like an outlier filtering. So when you train this correctly parameterized data network on this outlier filtered data, an outlier filter here means that it's hard for these networks to predict that value. You get a better network that's both efficient and also not over parameterized. Okay, so let's move on to the last topic, which is representation learning. So in classical computer vision, we already knew about David Ma's primal sketch idea, which is kind of hand-engineered feature sets that are progressively higher in degree of abstraction and also progressively more invariant, meaning they capture less about the specifics of the position and color of the pixels and more about view independent and sort of context independent features of the object. Then what inevitably happens in deep networks is that, so what this network shows, by the way, is a series of convolutional filters. We'll define those pretty soon in the course. These boxes are the network's internal representation of kind of a block of features. The features, so each block has kind of got XY coordinates related to the image and then a depth coordinate, and the depth represents different features. Is that making sense? Not super important right now, but anyway, you go through these layers of representations before you get to the final output. And it happens in the case of computer vision, but not in general for many other types of problem. But for computer vision, we actually do end up with pretty interpretable feature sets being learned by these networks. So in the first layer, the first graphic there, the thing that says neural receptive fields, this is an encoding of the actual weights of the filters that are being applied. And don't want to say too much about that right now. We'll talk about them later. But they can be both positive and negative in general. The other graphic below that, the bigger matrix of little images, those are the image patches from the real training data set that most activate those particular filters. So anyway, so here you can see it's shown as a little array here because there are actually 9 different filters. Each image within the 3x3 array is a particular filter and its coefficients. And those filters respond, you can probably intuit that when you have filter coefficients that are diagonally aligned, positive and negative, they're very sensitive to edges in the image with that alignment, and that's what you see in the layer below, image patches with strongest response. Okay, anyway, but you can make sense of those, the first layer in terms of those low-level filters that are directional filters, edge filters, really quite similar to the primal sketch idea. As you go up, you start seeing more high-level patches. These again on the left, these are the actual, well, effective filter coefficients because these are not filters anymore. So even defining what those are is a little more complicated, but they're roughly like filters. And these are the patches that most strongly activate particular neurons in those layers. So you can see that depending on where you look, you get more like stripe detectors. You're starting to get some circle detectors. So, and they're also not completely obvious, but the sizes of the areas of the image on the right are starting to increase because as you go deeper in the network, the cells see more of the image. And that's, it makes sense in terms of them being able to respond to higher level features. And then let's see, where a third layer, you're starting to see quite a lot more complicated things, these kind of honeycomb shapes, some wheel and circle shapes, and some people shapes down there. So, going systematically through those patches, you'll see that some of the patches are quite interpretable in terms of what kinds of things the cell is responding to, but some are not. And challenge with deep networks is that as we go further, the number of less interpretable features is starting to go up. So the network's really learning and understanding about things about the image that it's hard to articulate. People do that too, which is an interesting challenge. Okay, and so now we'll just go a little bit faster, but now you can see that it's really starting to recognize even higher level things like these are all dogs here. Yeah, flowers and flower-like shapes and people over there. All right. So, but in dramatic contrast to David Ma's approach, there was no hand engineering of these features. So the network had to figure all of this out from the loss, which is the label loss. So for ImageNet, you take an image in and you give it one of 1,000 classes like dog. In fact, they even have breeds of dog building, car, bicycle, etc. It gets that, from that single label, it gets an error signal. Basically, well, the error signal has 1,000 components to it because there's one correct answer, and it gives a negative gradient, I guess, to all of the wrong answers, and a positive gradient to the correct answer. That propagates back, as we'll see. Essentially, it computes the dependency of that output on all of the parameters through the network and improves the network. So it trains the entire thing from just that output signal, and that's what end-to-end training means. And but a consequence of those features actually being quite good general features is that you can train such a network on the ImageNet data set, which is big. It's got about 1 million images in it, and that's enough information to really sort out all of these parameters. But at least for most of the network, almost to the output, those features are good general features. They're not specialized to the classification task. So you can do this trick called fine-tuning, which is just optimizing the last few layer weights for a completely different task. And that's been a kind of a hallmark approach in deep networks. It's a known technique, it's an obvious technique, and it was available for years also in general machine learning, but it generally didn't work. because general machine learning really wasn't able to capture these general features as effectively. Yeah, question?
So are you essentially saying that the convolutional layers, the front ones, they're essentially going to be similar for different tasks, but the real kicker is the last couple of fully connected layers that can be fine-tuned for different tasks?
I wouldn't call it the kicker. It's incredibly important for the application task, but so is the front end, you know. And the most recent revolution in natural language processing, the BERT and ELMO models do the same thing. In fact, they actually do the front end part with unsupervised. They use unsupervised loss, and then you just fine tune for all kinds of tasks. And they do it simply on a even much more massive amount of data.
When you say front end, is it the first few convolution layers?
Well, for the front end, I mean, yes, the first 80% roughly of layers or something like that, yeah. All right, so to summarize, the deep networks have this layering of simple units which helps them learn a hierarchy of representations. You can learn that end to end, so you don't need hand engineering, just an output task. They improve with data. Somehow the representations seem to be the secret, that it's learning these very good representations to getting better accuracy. And it suggests also that they continue to improve as you are able to give them more data. Okay, and for that reason, they don't seem to have obvious performance limits as much as classical methods. They just keep improving representation and loss as you give them more data and parameters. Yeah, you can reuse them by fine-tuning. Multitask learning is a similar idea. You just train at the same time on the two tasks with different outputs. Okay. All right. So we'll continue next time. At this time.
Sorry, Tom.
No worries.